I thought I should create a project, wipe code some hardware, and check how credible AI can be with respect to generating hardware. Because creating hardware, logic gates, resistors, transistor, providing them clock, and everything being correct is really difficult. Let's see how effective it is with hardware. I've just given a instruction to ChatGPT to create a detailed README file for Claude. I just spoke this. I just asked us to create a RISC-V CPU with AXI, GPIO, and UART, a minimal one, and then maybe we can extend it later. So Claude has read the README and it has asked me, do you want me to go on creating 5-stage pipeline now or just create single cycle first? I'm gonna say create single cycle first because that's safe. Let's go step by step. I'm gonna go SystemVerilog because that's what I know more of. So let's go with SystemVerilog. Simulation toolchain. Oh no. I'm gonna go with ModelSim. These are all the files that is already created. SystemVerilog files. There's test bench as well. Implementation pan. There's memory, and everything is ready. And I'm gonna start checking. Stage A is underway. The first 3 CPU leaf modules are built, documented, and verified. All tests pass in my sandbox. I don't believe that for some reason because I want to check it on my own. Next up per the plan, immediate generator, then control unit decoder. Want me to continue or review these first? I think I'm going to review them. Yeah. So I asked it how do I run and see waveforms exactly in ModelSim, and how do I give command something like 3 plus 5 to check output is 8. Running with waveforms in ModelSim. Open ModelSim, menu, file, change directory, select this in the script, run this, paste. It should run ALU. There are waveforms. How can we check now? A is 5, B is 10, result is 15, operation was add. Let's go where the operation is changing, which is here, -8, which in binary is 1000, which we can see here 1000 is subtract in SVH file. A new operation here is 0111, which should be AND. So it should be ANDing A and B, and we should be seeing the results. So we can check ones and zeros, they are being ANDed. You know the AND, it's a normal logic gate. So ALU is working fine. I'm just gonna trust it, and I'm gonna assume program counter and register file is also good and it's tested. Okay, I tested it and ALU seems pretty good. So now I want you to go ahead and execute the next things in the pipeline of RISC-V core. Honestly, it has churned out a lot of code, and some of it I understand, some of it I don't. It has built a control unit, told me what output signal are, the design decision that it took, and how it verified. I understand that part. What is the current state of the project? How can I test it? In baby terms, what's happening until now? Oh, okay. So as of now, it has created program counter, register file, ALU, immediate generator, and control unit independently. And it has tested them independently. It hasn't created the top module, the control path. It has created the individual module, but there's no data path or controller which binds them together and tests the entire RISC-V based CPU core together. So I'm just gonna go ahead and give it a go to go on and work on next. Well, it just created a RV32i based RISC-V based CPU. For those who don't know, RV32i is the most minimal form of RISC-V instruction set available, open source. Next stage is to build an AXI4 Lite bus, then GPIO, and then UART. What capabilities the current RISC-V core has? What all things can I do in general, apart from small things like addition and subtraction? A real general purpose computer, a tiny one, anything that can be expressed as an integer, math, decision, loop, memory, it can run. That's decisions and loops, branch if equal, branch if not equal, plus comparison, functions, call, do, arrays, buffers, stack, lookup tables. Wow. So basically I've made a small processor. So I'm just running the core right now. There should be a waveform. Holy shit. Okay, there's a lot of stuff we need to check, but basically this is the test bench for the core that it just generated, and we're gonna test if what it actually has done is correct. It also has created test bench on its own. This is general test bench, so there are some test sequence. It will be running and it will check if the value is being loaded and if the operations are being performed. I don't understand all of the code and all of the files, but that's the beauty of it. You don't need to understand everything because Claude or AI now does a lot of stuff. You just need to know how this pipeline is supposed to work and for what input you see what output. So you need to understand the logic behind it. You don't really need to understand every individual file and what's going on inside them. You know, that's the beauty of it. You can see it's 1:14 a.m. So yeah, I'm gonna sleep. We'll come back tomorrow.
Several days later,
it asks me to load sim.modelsim directory and run this .do file. Let's see how it goes. Transcript prints each program as it runs, then the wave window shows CPU gut. Add this variable into the watch window and watch it counts from 0, 4, 8 and then suddenly jump backwards when a loop branches. That's the jump branch if not equal working. 19 checks pass, yeah. Inside DUT under core top program counter. This variable, it goes to 0, then 100, then 1000. It's just better to change it to just 4, 8, 12 and then it goes back to 4, 8, 12, 16. Yeah, it went back 5 steps, which it was telling us that it's gonna branch to last 5 steps. It's gonna branch back 5 times. For example, it has asked us to create my own program and run it. RISC-V core is some hardware. Hardware doesn't know software language yet. So we have to convert our code into a machine level language, which it will understand, which is assembly level language. We're gonna compile it, create a hexadecimal file, and then we're gonna send that to our RISC-V core. Inside this SW folder, I'm gonna create a new file. We're gonna add the code, save it, run it in terminal, build it into an hexadecimal file. Program 6 multiplier .hex file generated. Then in core test bench, which is the integrated test bench of everything, we just have to add this, run 7 times by repeated addition. That's the program in this file. Before the summary block, add save, go back to ModelSim, let's rerun this, enter. It's gonna load everything again, and this time 20 checks should be passed along with the one that we did. So yes, it says 20 checks passed, and what else should it see? You should see 26 passed, put check, press 3 in on purpose to see a failure. Yes, enter this. There definitely should be an error this time when we run it. There we go, there's an error. This is like the worst testing way, but I think it's okay. I'm just trying to build it completely and I'm relying on Fable 5. Let's build next stages. What my future aim is for me to create some kind of software and then flash it onto my RISC-V CPU core and see it working. The output is ready. I had my dinner. Meanwhile, AXI 4 Lite bridge and interconnect is created. It also created RAM, which is memory, UART, GPIO, and created 2 programs in assembly language code, which is machine code, which the core or CPU understands. It's quite impressive what it's done. Here is the machine code in assembly language .s files. Currently, Claude is writing machine code and it is being sent inside the memory, instruction memory. We don't want to do that. We just want to write easy firmware. We want to write software in C and then flash it inside the CPU core.
For example, if software is written in C language, there's a .c file. Our hardware, which is written in .sv files, and it's all logic gates here. You know, this is all logic gates. There's NAND, OR, XOR, everything. So these are all logic gates here. It's currently not able to understand this C language. It won't go here. We need to create a kind of a system where the C program is understandable by our CPU. For this system to build, we need an on-chip communication protocol from the ARM family. I have worked with AXI 4, there's AXI 5 as well. I'm going to use AXI 4 Lite. If there is an AXI Interconnect, this gives our CPU the ability to talk to external things. The C file, when it's compiled, it gets converted into machine code, and then this machine code sent to CPU's instruction memory, and then this instruction memory runs C code, and whatever we are trying to achieve by that C code is sent by this AXI interconnect to outside world.
Let's go with the alternative RTL approach which you suggested. Next time I can just write C code and the internal compiler will compile it, and machine code will be automatically generated and flashed into the instruction memory, and I can see it running in my actual hardware CPU. It took around 22 minutes. It has complete RV32 instruction set architecture, all of them. There were some missing instructions, and now it has it. Load, store via LSU module, and some 4 remaining branches. Now there is a timer peripheral, UART receive path, there is a linker script which is matching the memory map. If I edit anything in the main.c file, it will be direct going into instruction memory. It is a kind of a microcontroller which I just built in total 4 hours in 2 days. I'm going to implement this on FPGA
several days later.
If I want to synthesize on RTX 7, I should have chosen Vivado. Vivado has support for all AMD devices, but this is I'm choosing Cyclone 5, which is from Intel. So I'm synthesizing in Quartus Prime. So when you change from one device and its supported tool to another device and its supported tool, then something changes. For example, the clock for both are different, so we have to make those changes with respect to UART, and then the polarity of pins. So it says everything is ready, and I just have to open the QPF file in Quartus and hit start compilation. So I don't even need to create project, set the top file and everything in this Quartus Prime. If you guys ever know who has used Quartus Prime, when you open it, you have to create an environment, create project setup, set up the top file from the project navigator, and then start the compilation. But since it has done it already, I'll just go there, QPF file. It's open, FPGA top is loaded, and now we can just hit compile all. Synthesis should be smoother. So I've just started the synthesis. There's a lot of hardware here, so it should take fair amount of time, like maybe 5 minutes, I guess. I said it might take 5 minutes. It's been 6 hours 4 minutes. It's 1:27 a.m. I just went to a party in the university and let it run, and it's still 78% done. That did not age well. I'm gonna let it run for the night. There's definitely something wrong. I think all the signals are trying to utilize same hardware, multiple signals trying to utilize same resources. Let's let it run. See you tomorrow. It's been 17 hours and it's still 79%. That's where the AI hits hardware wall. You see the RTL code is being generated and you get happy by AI's work, but with respect to real hardware constraints, how accurate it is, how good it is, you never know. So you have to test it out by yourself. So that's what this experiment was about. And we see here large amount of conversation. Fitter, place and route has been running on for 17 hours. I'm thinking it's definitely has to do with the resource management, the hardware that the code is utilizing. Can you explain why this might be happening? What can we improve to make it better? And my instinct is correct, it's resource management. The summary shows that total registers 34,000 are being used. I mean, there are a lot of LUTs being used. Physical block RAM has no asynchronous reset, so Quartus conclude not RAM and falls back to registers. So instead of creating RAM, it created all registers. All the registers were also mapped as flip-flop. Claude is realizing it made some mistakes while making the decision of architecture of the design. An experienced engineer, let's say, would understand not to do that. Let's see what Claude comes up with now. QPF file. Now I'm going to click on synthesis. Now hopefully this time it will take 5 minutes. Last time I said that it did not age well, but that didn't work out. I think I jinxed it. There are a lot of congestions. Those are the warning messages. I'm gonna select them all, paste it here, check the code, and resolve for hardware. You start from the scratch looking at your hardware, the way you have designed and taken all the architectural decisions to create registers, flip-flops, RAM, and memory, instruction memory. Please take a look at it again. So as per Claude, it has fixed and tested on its own as well with 4,000 checks. It understands that there is some progress from the last iteration to current iteration. I'm not gonna say it's gonna take 5 minutes. Let's try. Well, we did it. 7 minutes. We have it. We have like a mini microcontroller unit. So we're gonna watch netlist. So this is SoC top, and all the modules and instances are inside. There's a GPIO, there's a bridge, RAM, timer, UART, XBAR, and core. Core is where instruction fetch, decode, memory write, these operations happen. It's basically the brain. And then UART and GPIO are something that we have created for our CPU to talk to the external world. And the way it will talk to the external world is with help of this XBAR, which is AXI Interconnect. So we used memory bits 65,536. We didn't use any DSP blocks. If we had an FPGA board, then we would have utilized 12 pins. ALMs 1400. This was the device that we used. I think overall this was a good project.